Hello everyone, this is Eileen Nan from Department of Civil and Environmental Engineering, University of Alberta, Canada. I am very happy here today to share one of my published work in AICHE annual meeting, which is roles of alcohol as a cosurfactant at brine-oil interface under a typical reservoir condition. You might be familiar with most words in this title other than the cosurfactants, so for a better further discussion, I would like to start with introducing what is the cosurfactant. The cosurfactant is a chemical used in combination with a surfactant to enrich the properties of primary surfactant formulation. The word cosurfactant might be rusty, however, the cosurfactant itself is actually everywhere in our daily life. Like in shampoo, makeup remover, and washing powder, we can always find a trace of cosurfactant. The cosurfactant has a wide application in commercial products in our daily life. Petroleum industry in specific, the cosurfactant is widely used in the enhanced oil recovery process. And here is number of citations by year with the keyword of cosurfactant and the enhanced oil recovery from the Web of Science. As we can see from here, the study of application of cosurfactant in oil recovery started as early as around 1990s and is still a hot topic nowadays. Commonly used cosurfactants include short-chain alcohols, alkandiols or triols, PEG or glycol ethers, etc., among which the most commonly used cosurfactant is the short-chain alcohols. Important component in various surfactant formulas, however, the role of the alcohols as cosurfactant is still not clear. Some studies suggested that the role of alcohols are decreasing the interfacial tension by standing at the interface. Some studies, however, stated that the role of alcohol is rather increase the solubility of the surfactant based on their observation that the introduction of cosurfactant do not always decrease the interfacial tension. Another interesting study stated that the role of alcohol is to increase the local molecular fluidity in the interfacial region by melting the unfavorable liquid crystalline structure. Based on these statements, possible roles of alcohol as a cosurfactant in the enhanced oil recovery can be classified as decrease the interfacial tension, thereby recover the residual oils captured by the capillary pressure, or increase the solubility of the surfactant to make the surfactant delivery to the reservoir more easier, or increase the local molecular fluidity in the interfacial region, thereby increase the stability of the surfactant front during the transportation over long distance. Important, however, the exact role of alcohol is still not clear. Therefore, the objective of this work is to investigate the role of alcohol as a cosurfactant at the brine-oil interface under a typical reservoir conditions. In specific, we would like to study their distribution, including where do they and where their functional groups distribute in the system, as well as how do they affect the distribution of other molecules. We will also study how do these alcohols affect the interfacial interactions by studying the change in the interfacial tension and the hydrogen bond formation. Finally, we would like to study their effects on the local fluidity using the diffusion coefficient as an indicator, knowing the fact that the molecular local fluidity is mainly dependent on the molecular diffusion. Here shows our system setup and conditions. We designed the system with rich brine phases sandwiched in between two oil phases. The dimension of the system in Z direction is around 20 nanometer, which is already proven as large enough to overcome the finite size effect. The temperature and pressure is set as 353 Kelvin and 200 bar to reproduce the typical reservoir conditions. We use the normal decay and 12 weight percent sodium chloride solution to represent the oil and the brine phase. SDS and propanol are chosen as the surfactant and cosurfactant as the most commonly used combination in the enhanced oil recovery. The concentration of SDS and the propanol in the system is based on the concentration which is used in the enhanced oil recovery process. And to study the cosurfactant effect, we gradually increase the number of cosurfactant in the system by changing it from 0 to 600. We use the CHOM63 combined with the modified TIP3P, which has already been proven to be the best force field for reproducing the structural properties of SDS among the most commonly used force fields. We also conducted a calibration in terms of density, interfacial tension, and we found that this force field is good to study the interfacial properties with this system. We put the SDS molecule at the interface for initial configuration, and the propanol molecules are originally distributed in the oil phase. After 20 nanosecond MPZT calculation, as shown here, we found that the propanol molecules, which were originally distributed in the oil phase, moved to the interface and even went through the interface to get to the brine phase. Here is the density profile for all of the molecules in the system. And for a better discussion, we use the 1990 criteria in which the oil and the water contents of 90% of their bulk values to define the interfacial region. And we color them using gray, yellow, and blue colors. From density profile, we could know that the normal decant and the water densities converge to their respective bulk values at the location far away from the interfacial region. And all of the SDS molecules are distributed at the interfacial region. And on the other hand, the propanol molecules, which were originally distributed in the oil phase, is mainly distributed in the interfacial region, and some of them also distributed in the oil and the brine phases. Such a dislocation of propanol is a good indicator to check the equilibration of the system. So here we gather the number density of propanol at the interfacial region and found that the number density of propanol reached the equilibration for the 20 to 30 nanosecond runs. And deeper color here indicates higher propanol number is in the system. And as shown here, the propanol density at the interfacial region increases as the number of propanol in the system increases. SDS and the propanol are amphiphilic molecules with functional groups have different affinity to the water. So to further study how they are functional group distributed, we classify these molecules into several groups based on their affinity to the water molecules. Take SDS, for example, we classified it into SDS oxygen head, SDS sulfur, SDS oxygen connect, and SDS tail. And the similar thing we went through to the propanol as well. And here is the functional group distribution. It can be seen that the SDS functional groups are closer to the water phase, namely the propanol functional group is distributed after that of the SDS. And for a better comparison, from now on, we have reset the value of the axis at the contact of the interface and the brine phase to be 0. Here is the SDS sulfur and the propanol oxygen functional group distribution as the propanol concentration in the system increases. For both figures, deeper color indicates the propanol concentration is high. As we see from here, the SDS sulfur functional group is supplanted from the interface as the propanol concentration increases. And for the propanol oxygen functional group distribution, we can see that the peak of it first increases as the propanol concentration increases and then gradually decreases after reach a maximum. We studied the interfacial tension changes as the propanol concentration increases as well. As we see from the figure, the interfacial tension decreases as the propanol concentration increases. And in order to further study why this happens, we analyzed the hydrogen bond formation between SDS water and propanol and water. We found that as the propanol concentration increases, the hydrogen bond density formed between the SDS and the water decreases. However, the hydrogen bond density between the propanol and the water increases. So based on this observation, we hypothesized that the decrement of interfacial tension by introducing the propanol might be caused by the ability of propanol to form hydrogen bond with water. We studied the effect of propanol concentration on diffusion coefficient as well. The blue column represents the diffusion coefficient in xy plane, and the light blue column represents the diffusion coefficient in z plane. As shown in here, increasing the propanol concentration do not always increases the local fluidity, and the local maximum local fluidity is observed at this system. And interestingly, we found that the maximum orientation parameter is also observed at this condition, which means the highest local fluidity is observed when the SD is more orientated. So here is the conclusion. The objective of this work is to study the roles of alcohols as a cosurfactant and brine-oil interface under a typical reservoir condition. And we have studied their distribution, their effect on interfacial interactions, and the local fluidity. And we found that the propanol is distributed all over the system. Their functional group is distributed after that of the SDS functional group. And the propanol can supplant the SDS from the interface. And in terms of interfacial interaction, we found that the propanol helps to decrease the interfacial tension, and this might be because the propanol can form the hydrogen bond with the water at the interfacial region. And finally, we found that the propanol does not always increase the local fluidity. And interestingly, we also find that the highest local fluidity is observed when the SDS is more orientated. So this is the end of my presentation, and thank you for your kind attention. And here is the author list. So if you have any questions, please feel free to contact us, and we will be very happy to have further discussion.